You can adjust the 20, and the 20 in here has an impact on the period, just like it did with sine and cosine. It'll impact it. So if I change these numbers, it'll change, how close together they are. Yeah. And then here's another one, a trefoil knot. So this is an interesting vector function because it's really difficult to see it here, but it ties a knot into itself.
That's pretty cool. I like that.
Yeah. And the vector function for that is in your book, but it's in here too. We'd have to look at it though. So here it is. Here's your x component. Here's your y component. Oh, no, wait. Oh, here's your x component. Here's the x component, the y component, and the z component. So notice they all involve some trig functions.
Is that going to be on the test?
No. It's just to give you some idea of some of the things that you can do. All right, derivatives. I have more good news. If you want to take the derivative of a vector-valued function, you just take the derivative of each of the component functions. And that's good news. Now, each of the derivatives of the component functions might require power rule, product rule, chain rule, quotient rule. That's all still fair game, but you do them individually.
That's really...
So what is the geometric meaning of the derivative? Now, we remember from Cal 1, the derivative of a function f, right? So if we take some function f and we look at some value at x here, then the derivative at x was the slope of the tangent, right? Slope tangent at x. That's what it represented. It's the pitch of this line. Well, now we're in possibly three-dimensional space, in which case pitches of lines aren't as intuitive as they are here, right? Here, slope, rise over run. But what do we have with lines in three-dimensional space that helps us get an idea of this? The direction vector, right? The vector gives it a direction. So somehow this derivative is going to hopefully generate vectors. And that's exactly what it does. Okay, so if r of t is a vector-valued function, then the derivative of the vector-valued function is another vector function. And given a value of t, then r prime of t is a vector which is tangent to the curve at the point r of t. So you're out there somewhere on this three-dimensional curve. You're going to that point and you're trying to find the direction vector of a line that's tangent to that curve. So let's go ahead and do an example, and I'll have a picture to follow up here. So find the derivative of this vector function. It is the vector function t sine t, t cosine t. You're going to need the product rule. So r of t is t. Everyone take a moment to do it. Go ahead, take 2 minutes to make sure you can get that derivative. Hey, did you eat? Can you eat? You should be getting this result here. You have to do product rule on each of these. And don't forget the negative sign. When you take derivative of cosine, you get negative sign. So, y'all agree? Okay, that is the derivative. That is the derivative. Now, it says find the vector tangent to this function, same function, at t equals pi over 2. So that just means we need to take this and plug in pi over 2. So what is r prime of pi over 2 here? So sine of pi over 2 is 1. Cosine of pi over 2 is 0. So this is just going to give us 1 out the front there. And then the second component, what do you have? So cosine of pi over 2 is 0. Then this is minus pi over 2. And then sine of pi over 2 is 1. So minus pi over 2. Okay. We've answered the first two parts to this. This is the one, though, that you need to be able to do right here, which is find the vector equation of the line that is tangent to that curve at this point. So we have to understand what we've actually figured out here. There's a curve, right? This is a curve in two-dimensional space. If we stop time at pi over 2, then this is the vector that would represent the direction, right? The direction of the tangent line. But this is in no way the vector equation of the tangent line. To find the vector equation of the tangent line, we actually need a point on that tangent line. We have its direction, don't we? So how are we going to get a point? We have to take pi over 2 and plug it into what? The original curve, right? Because remember, we're running tangent to the curve, aren't we? So what we need to do is, imagine you're drawing this curve, and at pi over 2, we found this direction. We need that point. So let's plug in into the original function. So this is our direction vector, right? Direction vector. And now we need a point. So r of pi over 2 to the original one, and you said that was what? Pi over 2, 0? This is going to be our r naught, right? And our general form of a line, this is basically the point that we use for the line. So are you ready for the vector equation of the line? Yes? Okay, here it is. Now, why did I use S of t instead of R of t?
So
R of t has already been defined, hasn't it? Yeah. It's the curve. I don't want to confuse the curve with the tangent line. This is our tangent line, right? So I called it S of t instead. So it's a point that's on that line, which is actually on the curve, and then the vector, the direction vector. Did I what? We're good? Sure? Okay. Any questions on where I got pi over 2, 0? Right, I believe I have a picture of this.
So when you put it together, it should be
Oh yeah, if I put it together, I didn't do that, but pi over 2 plus t, and then minus pi over 2 t. There you go. That would be it. I've always thought that this is an interesting function. T sine t, t cosine t. Do you recognize the sine t, cosine t part? That should draw circles, right? So let's just say that this was 4 sine t, 4 cosine t. What would that draw you? Circle radius 4? Or yeah, 4? No, it would be the radius in there.
yeah, the radius.
And then what if this was like, 10 sine t, 10 cosine t? Circle radius 10, right? But this number in front is actually not fixed. it's growing, isn't it?
Yeah.
So what would this draw you?
A funnel.
A spiral. It's two-dimensional. So imagine that the number in front is like your radius, right? So at the beginning, you're going to have a small radius, and then as t gets bigger, the circle gets bigger. And so what you get is this spiral. I hope I have the picture.
Would it be the same for a three-dimensional?
There it is. For three-dimensional?
Yeah.
Like if you had t, cosine t,
Yeah, pretty
t's.
much what we did here, would it be the same for three-dimensional? Or
Well, it depends on what you want to do with that third component. Like, what do you want to do with it?
If z was free, then it'd just be a spiral.
Yeah, if z was t.
Or z was t.
If z was something like t, then it would draw you, starting from the bottom, it would start to go outward, bigger. Yeah.
Infinitely more.
Yeah. But here it is in two-dimensional. And so you start out, and you move around. Oh, let me come back here. Let's slow this down.
it's like she's
What I have the computer drawing here is not only the vector r of t, which is the black vector, which gets you to the point, but also r prime of t, which is the tangent vector. So you can see how the r vector, the r prime vector, runs tangent to the curve the whole time. And what we were trying to find, what we just found, was at exactly pi over 2, which is, I don't know, where is pi over 2? I guess I'd have to type it in here. Pi over 2. Okay, at exactly pi over 2. Oh, that didn't take that, did it? There we go. If you go to exactly pi over 2, then where will you be on the curve? You'll be at pi over 2, 0, right? The vector that is tangent there is the vector 1, negative pi over 2, which means you go out 1, you go down pi over 2. That's this one, the red vector. Then we found the vector equation of the line, which is going to draw the whole dotted line right there. That's kind of everything we did together in one picture. Make sense? Okay. How what? Uh-huh. Good question. How can we apply this to in Cal 3? How do we? Well, in Cal 1, we use that slope a lot to try and find optimum solutions. So, like, what we do is we graph something, and we try and figure out where the tangent line is 0, because that would give us like local maxes and mins. We can do the same thing on a surface. So imagine, a three-dimensional surface, and we want to try and find the highest point on it, or the lowest points. What we can do is, instead of imagining a line on top, imagine a plane. Okay, so if I have a surface, imagine a plane running tangent. As you're moving around the surface, you've got this plane that's running tangent. If you can figure out where that plane is flat, right, then you will have figured possibly a maximum point or a minimum point. Same sort of idea.
Change which plane you're using, like y-z plane or xy plane, to kind of see like you can also get a max and min.
The other directions too, yeah. Yep. But to get the planes, what we're going to need are vectors that run tangent to the surface. And that becomes difficult. So imagine a surface, right? And what you do is you can imagine a curve going across it one way, and then a curve going across it the other way. And then you look at two tangent lines. And if you have two tangent vectors, if you have two tangent vectors and you cross them, you've got a normal vector to a plane. That's where we're heading, if that makes sense. It's a lot to say. I don't know if you catch all that, but it is going to help. All right, so also we have this idea of what's called a unit tangent vector. And all this is saying is that if you go back to this picture that I just had, we have the black vector. Is my black one still there? No, I took the black one off of there. But I had the black vector. It's no longer there. I had the red vector is the derivative. Okay, it's a vector. But since it's a vector, I can always find a vector that's pointed in the same direction that has a unit length, a length of 1. So over here, See my red vector? This purple one's pointed in the same direction, but it's just always maintaining a length of 1. That does become useful again later.
So why does the length of that tangent vector change?
Because that actually is the speed. That length of that vector is going to turn out to be the speed of the particle.
So is that essentially the same thing as like the normal vector to a plane?
Not exactly, because the normal vector to a plane doesn't have to have a length of 1.
Doesn't have, yeah.
Yeah, it doesn't have to.
So that's why in physics our first year velocity and then the acceleration.
Yes. Yep.
Because like if you figure t is time as it's going, it's going to speed up, and then that vector would.
We're gonna look at an example here. I don't know if we'll get to it today, where we're going to draw the same exact curve with 2 different functions, and one of them is going to have a longer vector than the other. And we're going to see that when we draw it, one of them draws faster than the other one, and so we can kind of understand that the length of that vector represents speed. All right, but here we're just talking about unit tangent vector. So given a vector function, if you take its derivative, you have a vector. And we can always find a unit vector in the same direction by just dividing it by its own length. This is something we did already. If I give you a vector and say, hey, find another vector that points in the same direction but has a length of 1, you would always just take that vector and divide it by its own length. So that's the definition of this capital T of t, is that notation means the unit tangent vector. So let's find capital T of t. Let's find it for this one. I don't know. How do y'all feel about that? I ask you for capital T of pi over 2, but how do you feel about capital T of t, just in general? This is going to be a little more difficult. Hang in, we're almost done. 20 minutes. We have to take r of t, which we already know, right? Well, is it r of t or r prime of t?
R prime of t.
We need r prime of t, which we got earlier. It was sine t plus t cosine t, right? And then it was cosine t minus t sine t. We've got to take that vector and we've got to divide it by what?
Its magnitude.
By its own length. Okay? So we get to take the square root of the sum of the components of that squared. And it's gonna be algebra. That's going to be sine of t plus t cosine t. We're going to square that quantity plus cosine t minus t sine of t, and we're going to square that.
Now, to solve
That is the definition, right? That's the derivative of r divided by its own length. So let's work on this part right here. Let's just work on this.
do we need to work that out?
We do need to work that out.
Or would it be easier if we just multiplied by the reciprocal? Like if we
Oh, like-
multiply by the square root of, that junk right there minus that other, just so we can get rid of it
Oh,
all.
like a conjugate?
Yes.
You can't, because this is addition under a root.
Oh.
If it was 2 different roots, we could do it.
There.
It's a good, but the fact that your neurons are telling you, like, do something to make that better is a good thing. But the conjugate just won't work here.
So since we're trying to find capital T at pi over 2,
We could have, that's what I was saying. We could have just plugged in and got easy numbers to work with, but what if you're being asked to find a formula for the unit tangent vector arbitrarily without being given t first? And so you need to see this sort of algebra, because this algebra is definitely within fair play for us. So let's square this. Let's do that on the side. Let's square that right there. What would happen if you squared this? Sine squared t plus 2t cosine t plus t squared cosine squared t. That's what you should get if you actually expand this out and collect like terms. What would happen if you expand this one out? So this one's here. This one, let's do that one. Cosine squared t?
what if it would be
Am I missing a t? Oh, I'm missing a sine t. Yes, sine t. Thank you. Paying attention. Good job. 2t cosine t sine t. I got the 2. I forgot the sine for some reason. And then now this one is 2t, same thing, right? Cosine t sine t. And then what would that last term be? Plus t squared sine squared t. And we're supposed to actually add those together, aren't we? Add these two together? Yeah, these middle ones are going to go away. Do y'all believe that? What's what's sine squared t plus cosine squared t? 1. So I've got a 1 there. And then here, what about this? That's just t squared. So these two terms, when you put them together, it's t squared cosine squared t plus t squared sine squared t. You could factor out the t squared, and then the sine squared and cosine squared will turn into 1. So all that just turns into that, doesn't it? And that's it. So if I come back over here, the unit tangent vector should be each of these components divided by that. So, and that's all underneath the square root, right? Don't forget we're underneath the square root on that. So sine t plus t cosine t over square root of 1 plus t squared. And then cosine t minus t sine t all over square root 1 plus t squared. Right here? 1 plus t squared?
Oh no, you can't take it out of the root.
Yeah, I can't take it out of the root. So that would be the general formula for it. Now, if you wanted to plug in pi over 2, you could. Just plug in pi over 2. Should we or no? Nah, we'll just leave it alone. What's that? Second derivative? Yeah, we do have the idea of a second derivative here, and it does have meaning.
That's its unit tangent vector, right?
Yes, this is the unit tangent vector. Now you'd have to tell me what t is for me to actually give you that vector. If we did 0 for time, we would get sine of 0, 0, 0. We get 0 here and 1 down here. So that'd be 0. If we did 0 here, we'd get 1. So at time 0, our unit tangent vector should be the vector 0, 1. And do you remember what that picture just looked like a second ago? We graphed it. It was like this. Remember that? And so at 0, your tangent vector was pointed straight up. So the unit tangent vector should be pointed straight up but have a length of 1, which is this. It's basically j hat, isn't it? Okay. All right. That's unit tangent vector. This is a three-dimensional. This is a vector function in 3D instead of 2D. This must be I must be really boring today. I'm putting my own daughter to sleep over there. You okay? Sorry, I had to drag my daughter along today. She wasn't feeling good. I really think she just wanted to skip out of school. All right, so vector function, find the vector equation of the tangent line to this point. So this is basically the same exact problem that we just did, except that it's in 3D. So I think I'll let you explore that on your own. I think this is what's more interesting to me is that it's a three-dimensional curve instead of two-dimensional. So
But essentially we do the same thing.
you do the same exact thing. Second derivative. So you ask, you shall receive. Second derivative of a function. So r double prime of t is just the derivative of the derivative, right?
Yep.
And it turns out that that second derivative gives us, we have a definition. It actually tells us something about the vector function, the curve. If a vector function, r of t, is given on some interval I, it is called smooth if the derivative is continuous. That means the first derivative exists on the interval, and if the first derivative does not equal 0. Okay, so this is not, second derivative's not in here, all right? But notice the definition here. If we have a first derivative and that derivative is nice within the interval, and if the derivative is not equal to 0 except at possibly the endpoints, then the vector function is called smooth. This is really strange. This is a strange definition because we've never really had this before. Let me draw a curve back from Cal 1. All right. What can you tell me from Cal 1 about the derivative at that point? The derivative is 0 there. What about the derivative here? 0 derivative here? 0. Okay. Would you say that this is a smooth function? Like, we haven't really technically defined smooth, but does this function look smooth to you? Like continuous, right? Smooth, nothing crazy happening here? But there's 3 points where the derivative is 0. But we would argue that, yeah, that's a smooth function. With vector functions, if your derivative is 0, you cannot say that you're smooth anymore. And that's weird, right? Because look at this definition. It says, a vector function is called smooth if the derivative is continuous and as long as the derivative is not 0. So if the derivative is 0 on some interval, it's not smooth. And that doesn't really match what we saw in Cal 1. Because even if the derivative was 0 here, we still had smoothness, but not with vector functions. 0 derivatives gives us a problem. We lose smoothness. So I think you need to see an example, don't you? Look at this one right here. Is this vector function smooth for all t? So what are you being asked then? Take the derivative, set it equal to 0, and see if you have any issues. By the way, back here, this should be a vector. Well, I'll change it later. But it's a derivative, right? This is a derivative. And that's the derivative vector function is a vector function. And so I can't say the number 0. I need to say the vector 0. All right, so we're going to take the derivative of this. What is the derivative of this vector function?
It doesn't necessarily mean that one of the components of the vector can equal 0. It's saying that it can't be 0 vector.
Say it again. It's not saying what?
It's not saying that one of the components of the vector can't equal 0. It's saying that it can't be the 0 vector at 0, 0, 0.
It's, yeah, this is saying we can never get the 0 vector. If we get the 0 vector, it's not smooth there. Okay?
In my head, it was kind of not making sense, like why we can't have the 0.
Yeah, we can't have the 0 vector. We can have one of these components be 0, but we can't have them both 0 at the same time. Is that the derivative of the first component? Yes. Little chain rule there. Now you can put that together too with a trig identity, but I'm just going to leave it. 4t cubed like this. So can you come up with a t that would make those both 0 at the same time? T is 0, right? What's the only t that will make the 0? There's only one answer here. There's only one real number answer. So 0, right? That's the only hope you have of making this 0. So now check 0 here. And you get 0, don't you? Mm-hmm. So at t equals 0, this was derivative. R prime of 0 is the 0, 0, which is the 0 vector, right? And that means this function is not smooth everywhere. You have a problem at 0. Okay? Now, would you like to see the graph of this?
What if only one was 0?
If only one of them was 0, that would be okay. Yep. So like, let's just say, I could probably make this happen. If for some reason this was like +1 here, then the only solutions to this would not correspond to making that 0. So you could get one of them to be 0, but not both simultaneously. So it would be smooth everywhere.
So with it being at 0 would
let me show you the picture first, and then we can answer your question. Okay, so here's the picture, and I will show you the tangent vector. Wow, that's too big. Here we go. There's the tangent. I need to go smaller here. All right, that should do it. And I'm going to pull this out of here. Please sign in. So right now, t is a negative number. All right, I'm plugging in a negative number, and look at the red vector. That's the derivative. The derivative vector. So as I get closer to 0, you see that vector, the red one? See what happens at 0? The vector goes away because it's the 0, 0 vector, and then all of a sudden, I'm here. And this is kind of interesting because when we were in Cal 1, when we were up here, the slope of the tangent line was what here? Positive, 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 then it went to what? 0, and then it went negative, right? But when we're talking about vectors, think about the direction of this vector here. The direction right now is pointed, you would almost say, almost 0 degrees, isn't it? Like the direction of this is almost like 0 degrees. And then what happens right after I get past 0, t equals 0? Which way is it pointed? The other way around, right? It's like it went from this to that. Now that happened in Cal 1 sometimes. We had these things called cusps, where your derivative would be what? Positive, 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 and all of a sudden, it flipped to negative, right? It also happened at corners like this. You would have a positive slope, positive slope, positive slope, and all of a sudden, it would jump. And we would say here that we had some sort of problem, that it's not smooth there, right? We have the corner. The derivative didn't exist here. Do you remember that in Cal 1? Derivatives don't exist at corners or cusps. We have something similar happening here. Our tangent vector is like wanting to point that direction. All of a sudden, something happens and it's pointing in the other direction. So we have a lack of smoothness there. Now, there was another question, was could we make this a smooth function? And the answer is yes, if we restrict the domain. So if we go back to this original question, and I change this, and I ask the question, is this smooth on t is an element of 0, 1, or 0, infinity? Now would it be smooth? Including 0. So we would need this to hold. Is the derivative continuous? Is the derivative continuous on this interval? So can you actually take the derivative and plug in all these numbers? Go back and look at the derivative. Could you plug in 0 into the derivative? Yes, right? The derivative was never undefined. It always had nice numbers. Cosine and sine and then t. So it's possible to plug in 0. Now, if the derivative is not 0, well, we know the 0 vector. We know that at 0 there's a problem, right? Yes. But it says except possibly at endpoints. See, 0 is an endpoint. So we could exclude that, and we would say that it is smooth on that interval. That was your question, right? So we could address that. We could also do this. We could do negative infinity to 0. We could do that interval instead, and it would be smooth there. All right, some of the things that we can take from Cal 1, luckily we can rest assured that all the rules that we had in Cal 1 follow through here with vector functions. We have that if you want to take the derivative of two vector functions that are being added, you can take the derivative of each one. We have that constants can come out. Remember, with derivatives with constants, they can just come out. We can do that. We also have a product rule. Okay, we have a product rule with derivatives. Now this is somewhat different. You have to be careful here. This is what we call a scalar function. And then, of course, u of t is a vector function. We can multiply scalars and vectors together. When we take the derivative of a scalar function times a vector function, we have the traditional old product rule. But this right here is scalar multiplication. Let me try and give you an example of this. If you were asked to find the derivative with respect to t of sine of t times the vector function t cosine t. That's what this is saying. You would take the derivative of sine times t, okay, plus the derivative of this one, which one was it? This, right? Maybe I should do that one. That's a little hard to see. I know I'm almost out of time here. It's the product rule, but you have to be a little careful with this. This one right here is our f of t, right? This right here is our u of t.
Before we take the derivative, can you just multiply them together?
Yes, you could just multiply them. Yes.
And just take the derivative?
Yes. Yes, but I'm just showing you the rule.
I'm just
Yes,
saying,
the rule. What does the rule say? So let's just try this. What is the derivative of f here? Cosine t. So this should be cosine t times u of t, which means just t cosine t, plus now f of t, which is just sine t, times u prime of t. So I differentiate this, right? So this will be 1 negative sine t. And now you can pass the cosine t through, pass the sine t through, group the two vectors together, and you'll have your result. That's what happens if you have a scalar function times a vector function. What if you have a vector function times a vector function? It's a dot product, right? Dot product. And then you have the traditional product rule, but now with dot products.
Does the quotient rule apply to?
That's a good question. Does it? It would depend on what your quotient was. And we don't really have the quotient rule defined here because you'd have to be talking, is it dot, right? Dot was a certain type of multiplication. We don't have an equivalent quotient. Like we don't have an inverse of the dot, so to speak. It's a good question.
With order of operation, if we do dot product, waiting for dot product.
Do we what?
Like, as I look at that, like, could you do the dot product as the same steps you do the multiplication, or you just wait and do everything else and then dot it at the end?
You're talking about this right here. Yes? Are you saying would you do this first and then take the derivative? Or do all this and then take the derivative? This is just a rule. It's telling you you can do either one. And then there's one for the cross product, and it's the chain rule, basically. I'm sorry, the product rule, again, with cross products. And then we have the chain rule. All that note is about is just letting you know that when you take derivatives, everything works as normal, as expected. All right, I'm just about out of time. I know y'all are really upset about that. This is kind of an interesting problem. We'll do that, I guess, next time.
Whenever we take the exam, I remember in part 1 and part 2 we had like certain pages we could use.
Certain pages.